Good evening, everyone. Welcome back. We now move on.
इससे मोहब्बत की जाए
We now move on to the plenary talk for today's session, followed by discussion. It is an honor to welcome Dr. David Langer. He is an emeritus professor in civil engineering from the University of Illinois. We also have with us Dr. Alexander S. Brand. Dr. Brand is an assistant professor in the Charles E. Weir Jr. Department of Civil and Environmental Engineering and an affiliate faculty member in the Department of Material Science and Engineering at Virginia Tech. He earned his PhD in civil engineering from the University of Illinois at Urbana-Champaign, where he also completed his master's in civil engineering. He also worked as National Research Council postdoctoral research associate at the National Institute of Standards and Technology, Gettysburg. His research interests are focused on material science of civil infrastructure materials, reaction and hydration kinetics of minerals, advanced characterization techniques to study the nanostructure development in cementitious materials, concrete pavement engineering, and so on. He leads the Brand Research Group, whose primary research focus is on cement chemistry, concrete and cementitious composites, but current and past research has also focused on geochemistry, corrosion, asphalt chemistry, polymer concrete, and non-destructive evaluation. I welcome you, sir, to chair this session and introduce Dr. David Langer.
Very much for the introduction. I'm very pleased to introduce our plenary speaker today. David Lang is a professor emeritus in the Department of Civil and Environmental Engineering at the University of Illinois, Urbana-Champaign, where he has been a faculty member since 1992. He has published over 100 technical papers and reports, and his work has received over 7,500 citations. Dr. Lang is a fellow of the American Concrete Institute and a fellow of the American Ceramic Society. He served as the president of the American Concrete Institute from 2018 to 2019. His research interests include the material science behavior of concrete materials, characterization of microstructure of porous materials, early age properties of concrete, water transport in construction materials, and repair of civil infrastructure. His presentation is entitled In Search of Eureka. Please help me welcome Dr. Lang's presentation.
Well, greetings from the University of Illinois. I want to start by thanking the organizers for inviting me. It's a pleasure to be with you in this conference. And as you see today, our talk is going to be In Search of Eureka. The idea is to address the discovery and the creativity of academic research, something we all have a part of. And I will be touching on my past experiences and some of my observations from friends and colleagues who I've known over the years in the field of concrete materials. So I want to start with building a foundation for our discussion. And some of the basic questions are, what is research? How would you answer this question? Well, you might say it's finding answers to questions. You might say it's creating new knowledge. You might say it's a systematic inquiry to describe and explain, predict, and control. You might say, as we would for a high school student, it's a scientific method, making a hypothesis and testing that hypothesis through experiments and analyzing the results of the experiments. All of these are, of course, adequate responses to the question, but there's a lot to it. And here's a research enterprise word diagram that shows that we have lots of aspects, including the teaching and the curriculum and the scholarship that is associated with our field. And we need a place to do this research. We have this place called the Research University. We have 5,300 universities and colleges in the United States, 25,000 around the world. And these places, some of which are dedicated to research, have the facilities and the equipment that allow people to do those experiments that we were talking about. So place defines function. If you have a place that's outfitted and equipped, people can come in and do high quality research. But research equipment doesn't by itself solve the problem or lead us to those eureka moments. Knowledge does not arise from brick and mortar alone. The eureka moments come from people. So it's a very human experience. And a comment about the word eureka, that of course comes from Archimedes. You remember the story that he's in a bath. He's been asked by the king to determine whether a crown is made of pure gold. And he's thinking about this as he lowers himself into the bath, sees that the water level rises. So here, a very irregular shaped object like his body goes into the water. He can see the volume very clearly. And now knowing his own weight, he can determine density. Density would tell him whether that crown was pure or not. And in fact, the way the story goes is it was not pure. So I think there was probably a problem for somebody who had provided the crown saying it was made out of pure gold. At any rate, Archimedes, upon making this this nice thought about measuring irregular shaped objects and volume and so forth, jumps out of his bath, runs naked down the streets yelling, "Eureka, Eureka, I have found the answer." And so we hope that our students experience that moment of excitement, and maybe not with running down the street naked. So now today's talk, what I did is kind of I was inspired by a TED Talk I saw by David Epstein a few years ago. He's looking at the progress made in sports, and he was making some observations about swimming records. It has 5 million views, so a lot of people have seen these TED Talks. And in this talk, he makes the point that the progress is not incremental and linear over long periods of time, but in fact, you can see perturbations, a step function. So we see several here. In 1956, the flip turn that was invented in this sport. And you immediately saw a lot of increase in the world record. And then in 76, there was an invention of a drainage around the outside of pools that diminished the turbulence as the swimmers come into the wall. And immediately there, we see a benefit in lower times. In 2008, there was an adoption of these new fabrics, the very low friction fabrics that allow swimmers to skim through the water. And that immediately brought down the record. So this perturbation creates an advance that breaks away from the linear progress. And we can see that even in our own academic work. We can bite away a little at a time, making progress on hard problems. But in fact, there are moments where we make bigger jumps because of equipment or new ideas coming together. And we'll talk about those kind of things today. One thing to ponder is how have we been doing as a field of academic research over the years? A few years ago, I was cleaning out my office and I had these old records from 1971 when the American Ceramic Society was being asked to form the new cements division. And Richard Berger, who is sort of my predecessor at the University of Illinois, was making the case for why we want to have this special division for cements research. And he cited some problems. Number one, the chemistry of anhydrous cement compounds. 2, the chemistry of cement hydration. 3, microstructure of hardened cements. Fracture of hardened cements. Number 5, new cement-containing composites. Oh, really? Those are really familiar topics. It's like we're still working on it. So some of these problems are really thorny, long-lasting, multi-generational problems that need continued attention. Another piece of data, still, this was on the same office cleaning exercise. I found documents from the PCA research labs in 1940s and 50s, studies of the physical properties of hardened cement, Powers, 1948. Or how about the rheology of fresh Portland cement paste, 1960. Or chemistry of hydration of Portland cement, 1960. Or estimation of phase composition of clinker in 1939. Or electrical resistivity of concrete in 1968, or one of my favorites by Pickett, 1946, shrinkage stresses in concrete. Wow, we're still working on some of these problems after all these years. Have we actually solved any problems, you might say? Well, let me assure you, yes, we have made progress. And in fact, these kind of moments of eureka have happened in my career, and I hope you identify with this idea that, boom, we've made some progress and we're breaking. So that's what I want to share with you today. Some of the observations of eureka that even in hard problem areas of science, that we can find advances that move us to a new kind of level. I'm going to give you 6 cases. So to make to build my thesis here, I'm going to cite 6 case studies of eureka. And you can see them here. We're going to start with hydration modeling, and then we'll work through the other 6 in order here. So let's start about hydration modeling. You know, back in that 1948 document, Powers had this diagram. And so they knew that cement grains had a proximity to them in the mixture of in the concrete with water and so forth, and that somehow there is an issue having to do with the chemical reaction taking place at the interface. And this diagram of these neighboring particles having a reaction through the aqueous phase was already conceived in 1948. And this was, of course, part of our understanding of how to make, concrete technology. But we needed a new idea to take us to a new level of understanding hydration and microstructure development. And we have these other diagrams very early. Here's a diagram from 1976, the conceptual idea that the hydration products are crystalline. They reach out from the particles. They interact with each other, forming strength and bonding to each other. But I think one of the eureka moments in this subject area had to do with harnessing computer power to solve the microstructure development problem. That was a hard problem. Sure, Powers had the concept, but he never solved the problem. And so to solve it, Klaus von Brugge was one example of making a model that is known as Hymostruck, and has had a good run of a lot of study that has come out of this area. But it solves the hard problem of finding where the products are, what their chemistry is, what is the volumetric exchange between the hydration products, between the original cement and the hydration products. So these models were developed. Another such example was Hamlin-Jennings and Johnson. They worked at NIST, but this was the simulation of microstructure development. And here the particles were all modeled as spheres. And so you would have overlapping areas that would react in their system. And you had to keep track of that from time step to time step to time step of how much volume was in this area between the particles and what you would convert it to in the next product. Talk about a hard problem of tracking that geometry in a three-dimensional volume. This was a complex database problem. We needed a better idea. And that better idea came along with other NIST researchers. Dale Bence and Edgar Bosey had this cellular automaton idea where you basically just build your volume out of voxels, and all the voxels have identity as being a certain kind of cementitious material, and the interface would determine what rules were applied for converting that in the next time step. So hydration would take place only at the interface, and the volumes would change from one product to another. The rules were very simple. The calculation problem was very simple. And so all the complexity of tracking spheres and little slivers was taken away. And we were thinking about a more simple, easy, faster way to compute this problem. A very successful idea that took the computer power and really applied it to make many new ideas move forward with regard to permeability, percolation of pore space, and so forth. Here's some more pictures from those early models. This is how you would, on the left, you see the structure they started with. This is a picture in 3D, or the volume is 3D, but you see the colors identify what phase is in the raw mixture of cement and water. And then with time, you see the time steps on the right, where you take the cement, you identify interfaces, you create ions in the open space in water, you react the cementitious reactions, and you create new product, which is shown in yellow then at the final right side of the diagram. So in the end, these pictures were strikingly realistic. And many researchers found it useful for advancing their understanding of microstructure development. Case study number 2, pore size measurement. This comes really on the heels of the last one. So now we have some better understanding of what pores are, how they're connected through space, and so forth. We have this early understanding of a complex microstructure. We know that particles of cement react and form the solid skeleton, and pore structure controls permeability, hence durability. How can we measure these with these microscale capillary pores that control strength and permeability? There was a very early technique called mercury intrusion porosimetry that was applied to cement research. And I used this back in my PhD, actually. And these diagrams are just here to illustrate the idea of what is the capillary pore between the layers of hydration product. And what we're going to see in this technique is that we take a sample and we pull a vacuum on a volume here, and then we apply high pressure, increasing pressure for the mercury to intrude into our sample. At the end of that experiment, we get a curve that shows you how the pressure is applied, how much volume of mercury went in, and then interprets this as a diameter of the pores that were intruded. And so this was somewhat of a non-contact, a blind way to measure microstructure, measure pore structure. And but for a while, it was the best thing going. And we wanted to look at that a little bit more closely. And we thought about, well, let's do it differently, because we really need to inspect these microstructures. Let's replace that mercury with Woods metal. Woods metal is a metal that melts at about the temperature of a cup of coffee, odd cup of coffee. And so we could do that safely. And then we could press that, apply pressure, and push that into the microstructure, and then hold that pressure while we reduce the temperature to allow the metal to solidify. And by doing that, we could get these step pictures. A pressure of 3.4 megapascal, B 6.9 megapascal, and so forth. And we then could slice these samples and use a scanning electron microscope to visualize where did the mercury go, or in this case, Wood's metal go in this microstructure. And you can see that by the time we get to 34,000, for 34 megapascal, we've got a fairly complete, widespread intrusion of the Wood's metal into the microstructure, and that helps us understand what was happening in the MIP experiments, and largely calls you to wonder about this because the results of the volume and the area that you see from the Wood's metal experiment from the MIP don't match, and they don't match because there's something called ink bottle pores. The pictures that we are taking with Wood's metal revealed a different story than the measurement of volume from the exterior of the sample. And it basically, in some regards, maybe what makes you wonder why you would want to do a mercury intrusion test. It's not a really very good way to measure sizes of pores. Okay, so this is a better way to measure sizes of pores. You get a nice scanning electron micrograph. This by Paul Stutzman at NIST. He's done some great work with getting good quality images, and it's a preferred method for measuring real features of microstructure. Case number 3, fracture. There was quite a surge of interest there still is some research on fracture, of course, but in the 80s and 90s, there was quite a bit of work on fracture because we were looking at this non-linearity, this quasi-brittle behavior that we see in concrete materials. The ones I chose here to illustrate the problem are interesting to me because this is the same material. The test on the right side is at 10 hours old. The test on the left side is at 28 days old. And of course, we all know the strength is very different, but look how the fracture pattern changes. The fracture is very different, explaining in part why the strengths are so very different. And this was when I was at DTU with Henrik Stang. So we borrowed, our field of study borrowed some ideas about fracture from metals, who created this idea of a process zone, a cohesive zone, where you have some ductility in metals. Well, we have something like that too. We called it a fracture process zone that needs to be conceptually there for us to understand why do we have a non-brittle, or that our perfectly brittle material behaves as this quasi-brittle material. And so this spun off a lot of ideas. And some of them needed to be investigated in a careful way because it meant that you had a field of strain or a stress distribution that was complex around the tip of a crack. How are you going to measure that? Well, the new eureka here is new methods to capture the strain field. And we've seen some very interesting things done with interferometry and photoelastic materials to capture the state of stress or the state of strain. This is really the strain distributions. And in ACBM, in those early days in the 90s, we had holographic experiments in digital image correlation as ways of getting this kind of result from a physical test. And the eureka moments here are shown as, this is a holographic experiment by Rich Miller. And we've really had quite a few different people working in this field. So I think these techniques for measuring strains off of the surface were very important for understanding how cracks move, how they propagate, and being able to just simply visualize the fracture problem. And those insights, of course, lead you to think about novel solutions like fiber reinforcement, When we are understanding properly what's going on at the tip of the crack, ideas about reinforcing that come into play, and you can start to be able to measure and verify the benefits that you get from fiber reinforcement, the distribution of stresses at the tip of a crack. Case study number 4, shrinkage. There's been a lot of study on external drying shrinkage. It's been a topic studied for many years, in part because it has such practical ramifications. Cracking of slabs, pavements, flat work has been a problem forever. It still is a problem. And understanding that problem helps us determine better ways of solving that problem. So the early ages of concrete involve some complex volume changes and chemical shrinkage. And even sealed concrete can exhibit shrinkage. So you see here some basic testing of a sample using a standard C157 test. And then I showed this mud field cracking as just an illustration of how we get curling and when we have a gradient of shrinkage through the thickness. Well, we certainly have seen some eureka moments in this field of measuring shrinkage. And I want to cite this very nice test that we built off of Springenschmidt's model in the 1980s when he was doing passive frame for temperature cracking. And then Arnon Ventur and Costa Kobler in the 1990s used this kind of configuration for restrained shrinkage. The actual test that I show on the left is from our test at U of I, a larger scale test. And basically what we're doing here is casting the concrete in a test configuration where we can apply a load and measure the shrinkage of the sample simultaneously. So we can control, let the machine control the test with strain. So the point of this is that as the material shrinks, we want to measure how much is the net stress, how much force is created, and then we can apply more stress to lengthen it as happens in a restrained sample. So this study allows us to think about how to characterize shrinking concrete and what is the early age cracking problem. Another eureka moment is in development of what's known as the ring test. This is a fairly common test now today. Jason Weiss developed this during his PhD at Northwestern, and it was basically just a case of taking a steel ring, making a casting concrete around that ring, and then once that concrete is cured, allowing that to age with time, and the shrinkage of the ring would compress on that steel. And believe it or not, you can put strain gauges on that steel and you can sense how much stress is being applied by the concrete. It's sensitive enough that you can just feel that and then clearly see when any cracks form. There's a release of that stress. So this test is pretty straightforward to run. It doesn't need a fancy test machine, and it's been popular for that kind of reason, that people throughout the materials testing field can do this test readily. Another eureka kind of moment was a test developed by Ole Jensen, a dilatometer for measuring autogenous deformation of hardened cement paste. One thing that's really hard about cement paste is that it's basically very weak material, and it's in those early hours, how do you measure anything about that material? So he came up with this idea of having a collapsible kind of an accordion-like form that could be filled with the cement paste. And then you have a regular length measurement of that form. And it turned out to be really effective for measuring the volume change of that early age cement paste. And one of the primary results that we see again and again now in literature is this autogenous shrinkage with chemical shrinkage. And we see the divergence when we start to get to that point of the skeleton is now stiffening and the autogenous shrinkage is no longer able to shrink because it's restrained by its own volume, whereas the chemical shrinkage is continuing due to hydration. And this area where you diverge is stress, where you have that the body of the material is resisting these stresses that are caused by shrinkage, and cracking can occur. So you have the spontaneous cracking, understanding how that's done, understanding how to measure the tendency of a material to undergo that shrinkage. That's a big deal. And it's even being put into specifications for some projects where we need to find low shrinkage cementitious systems. So this was a good citation, autogenous shrinkage in high performance cement paste that with Pietro Lura, another one of my good friends. And so he's, that'd be one for you to look up and refer to. So this eureka kind of moment inspired many additional things happening in shrinkage. We've come up with different kind of specialty devices, and I've seen this kind of excitement about discovery in my own students. We had some students, Sala Altabat and Zach Graisley, Chungjun Lee, Matt D'Ambrosia, Dan Castaneda, over many years in different kind of topics and different kind of configurations. They were trying to find how does shrinkage affect the performance of a system. And perhaps one of the things I can point out here that we kind of brought to the story is this better methods for measuring relative humidity gradients. So we can get that gradient problem figured out a little bit better and see why curling takes place or how to quantify it. And that's, I suppose, one of the other things we kind of emphasize is building models that could predict these kind of field level observations like curling and cracking in the field. Case study number 5. 3-dimensional. So a lot of these same things we've been thinking about with microstructure in 2D, we want to move to 3D, and anything that can help us do 3D is good. So 3D itself is a eureka moment. So we've seen this advance. You know, when I was a younger student, I thought scanning electron microscopes were really terrific. I still do think they're terrific. But X-ray CT, computed tomography, is the next generation of terrific. And we saw this area advanced first by people with access to the national laboratories, where we had synchrotron X-ray sources that were used for computed tomography experiments, which is great. Fine, they're a powerful X-ray source, and the tomography equipment was high quality, but you had to go to a national laboratory to do these things. And we always were one that was looking for easier ways to get things done. Well, so there's this new generation that has come along with smaller and more affordable X-ray CT equipment that brings the capability into our own university laboratories. And by this time, a lot of you listening to this talk will say, yeah, we have that on our campus too. So these have been all the rage, that we've got new X-ray CT techniques that could be used for cement studies. And here at U of I, we have these, well, we have other ones now, but at the time I took these pictures, we had 3 machines. 2 were called micro and 1 was called a nano CT. And here's some pictures of how we ran this experiment. Well, first, to the uninformed here, you're using really, really small samples. So you can see on the lower left, the little chip of material is going to be our sample holder. And we put that into the configuration on the right, where we have the X-ray source coming from the left of that photograph, or from the left of the photograph toward a sensor on the right. So the other important thing is that your stage rotates. any one position is just like an X-ray. So you're getting a shadowgram of your sample. But then you move it a degree or two, take another picture. Degree or two, take another picture. And you it rotates around 180 degrees, and you're getting every angle on that. Now you take 180 images and you throw them in a computer and ask the question, what was in the middle of that sample that explains simultaneously all those 180 images from the different angles that we took pictures? And it does that hard problem, and it comes up with a picture that shows you the three-dimensional reality of density in your sample. So we did some where we were creating an interface with a gold foil, and you can see here we have two pictures, one after 3 days, one after 28 days, where we found a way to take our sample and ensure alignment of the orientation so that we could get a match of the images at 3 days and 28 days. So that was part of what we were trying to do. And in fact, this was maybe one of the more useful kind of results, because this is the image, remember, is three-dimensional, but these are two-dimensional slices that are aligned and matched with each other over time. We have 1 day, 3 days, 7 day, 28 days, all shown together. And so you can see up in the top left, we have a particle. Now look how it has changed by the time you get to 28 days. It's gone. It has been that light area, a high density particle, is now a low density void. And it's because it's dissolved and it's hydrated and been part of the hydration process. This dark area by the yellow circle is filled in. So the hydration product has been deposited in that otherwise open area. Down here, there's a particle that doesn't change. Not every particle does react and dissolve at the same rate. Here we have a particle in green that now has a void, or not a void, but an interface that is particularly high porosity. This was termed by Sid Diamond as being a Hadley grain in honor of his grad student that wrote up the study that kind of identified that feature. So grains have been known to kind of create these hollow interfaces as that depletes of the dissolution is not even through the microstructure. So all these kind of features about microstructure change could be studied with these kind of three-dimensional techniques. And that is a eureka kind of moment where we have really a very powerful way to look and track these things that fit back with the modeling done by NIST and so forth. All these three-dimensional techniques kind of should come together, and they have come together. Another way to use these techniques is to use the microstructure from CT and track its porosity and transport. So in this case, we had a partnership with Klaus von Brugel and these researchers Ming-Zheng Zhang and Yangjia He and Guang Ye. These are colleagues that were working at Delft, and we gave them our files that had the microstructural information, and Ming Zhang and his PhD did a study of basically doing a computer model of diffusivity, mass diffusivity through this volume that he now could see and create measured by micro CT, and then he had some laboratory studies of diffusivity and was able to see good correlation between what the models could predict and what the physical experiments were measuring. And thus it confirms that the assumptions made about diffusivity and the assumptions made about what you're doing in your laboratory experiments are in fact validated by these kind of combining of techniques in the study. Oh, the other last thing we can do with a CT is if we have this digital image of a microstructure, we can enlarge it 500 times and print it in 3D, print it with a 3D printer. And so that is a model of a microstructure we were studying that had to do with foam materials. The last case study I want to offer today is modeling fluid behavior of concrete. You know, rheology has been just a huge topic over the period of time of my career. Early on, I wasn't particularly that involved in that too much, but as self-consolidating concrete came along, I became more involved. And there's some great people that I have come to respect highly in this field of fluid understanding rheology. Nicholas Roussel is the editor of this particular book. You could get this book. This is a terrific book. It has all the stars of the field. Robert Flatt wrote a chapter in there. Kamal Kayat wrote a chapter in there. And anyway, there's many applications that need better knowledge about rheology, self-consolidating concrete, flowable fill, pumping. Dimitri Faze is an expert on pumping, and he certainly needs a lot of information about rheology. And then 3D printing. And only about 1,000 people around the world are working on 3D printing experiments, and so they need to know about rheology. And I think this is basically where we need to go from here. There's a lot of people doing the practical, a full-scale even testing of 3D printing, and we need now to understand how to predict the behavior of these materials to basically design 3D mixtures that work really well for 3D printing. And let me show you an idea about that. Well, first we're going to look at some pictures of the magic of concrete technology. I just get a kick out of this slide because we have a paving machine with concrete holding its own shape immediately. And on the right side, we have a self-consolidating concrete material self-leveling itself. And it's all concrete. Maybe not even that very different in mixed design, really. It's just perhaps a few changes and maybe adding some chemical admixtures. But it's an amazing material, and that's what draws us to work on it. And very practical, meaningful, economically important questions are being answered with our research. Well, this area, of course, we already know that concrete is a complex granular material, and granular fluid. There's a whole field of study of granular fluid modeling, and this allows us to find how the size of particles, the nature of the chemistry in these systems, how they result in the viscosity and yield stress of the material. And we've been doing some fun work with discrete element modeling, discrete element methods. The structural folks know finite element methods well. And this is where you have a large structure modeled by small elements that have connection to each other. And so all the connecting points have to be resolved in terms of forces and displacement. And that's what the computer is going to do for you. So you have this continuum mechanics paradigm for thinking about finite element method. In the case of DEM, we have a whole bunch of individual discrete particles. And so the rules that are governing are neighboring rules. How does this particle relate and impact its neighboring particle? And that is a whole different concept, but it can now give you the possibility of modeling fluids. And so our neighboring particles here are shown on the left. We see sort of a spring and dashpot model. In fact, two of them. So we have a spring and dashpot model acting through the axes, and then we have a spring and dashpot acting as sort of in 90 degrees to that. And so between that, we have the combination is what we call a model for a liquid bridge. And so you see on the right, this idea of a meniscus and capillary forces keeping water between a particle and a surface. That's a familiar idea. And how the character of that the radius of that meniscus is related to the resolution of forces in the problem. And that's what this spring and dash spot modeling can do for us. So we can find how to put in coefficients in these terms needed by the model to get the right capillary force contribution for a wet particle, a damping contribution, frictional contribution, elastic contribution, all together to get the right overall behavior. And when we do that, we get some powerful opportunities. And so in this case, I have I chose to model a rheometer itself, and you can see we're getting a real-time result of the moment exerted on the vane. And why do I want to model a rheometer? Well, because my tests are coming from rheometers. So when we have a test in the lab with a rheometer, we have now a model that can hope to mimic that. We can see if we're being successful at capturing the behavior. If you are successful at capturing the behavior measured in the model, well, you can start going to model many other configurations. You can have it flow in different ways, but you use all the same parameters because you believe them to be true. So in this case, we have on the right, you see the flow of 3D print head, kind of crude, but it just shows you the example of what it could do for measuring how the flow of gravity, that's all that's acting on that part of that material is just gravity flow out of a nozzle and how it can be shown coming together. On the right, on the left, we have two different sands that pile up differently because of being wet or dry. So the contact forces are different for these two. And you can see one's a tall pile and one's not a very tall pile. So DEM has proven to be very powerful. And I think we're going to continue to see pretty profound understanding coming from these models. So the Eureka, when we have these successful models, these models now can serve as design tools. What are the properties we need in our materials to successfully complete 3D printing problems? Well, we can go into the lab and we design materials to give you those properties. Linking the laboratory experiments to field performance is a prime goal, and DEM can do this for fluid concrete. And we can do this for our 3D printing in the computer. So that's certainly convenient. And once we have confidence in the model, that can serve as a design tool for making new different mixtures for 3D printing. So that's the end of my 6 examples. And now we're really interested in this idea of Eureka. How can we institutionalize Eureka? How can we make it easier to get to that experience of discovery? And the first thing I'd say is we need to think about teams. That we've seen so many examples where teams have been a successful catalyst for helping advances take place. I mentioned ACBM several times. That was a center started in about 1990 and ran through about 2002 with government funding, NSF funding, and you'll still see references to ACBM today. I served as director of the Center of Excellence for Airport Technology. We worked with O'Hare and had some very nice projects moving through that center. Recast is Kamal Kayat's research center that I participated in with him. But I also wanted to list ACI and RILEM and American Ceramic Society. These are 3 organizations that really do a great job of being a host to the community of researchers. So we have those conversations. This is the kind of idea, when we're talking together, then we're going to get the Eureka ideas. And that's such an important part of making progress. So some problems are timeless, just as Pickett was working on shrinkage 50, 60, 70 years ago. We're doing it still today. Every new generation revisits some of these old problems with new technology, greater computing power, and the benefit of being able to read the literature. Don't forget to do that. and I'm sure Eureka will be heard in the future. Our progress will continue. Eureka. As sort of a closing comment from the Journal of ACI, April 1949. Part of mine is this walk down the history lane here. This is a nice quote. When shall we take concrete from the specialist, that is the microscopist, ambitious scientists and chemists, and give it back to the engineer? I see the answer very clearly, and the answer is never. That breed of engineer, the pick and shovel, transit and level type, has become an extinct species of animal. This is written by the president of ACI in 49. And I agree with this. This is it's just sort of a statement that our field, concrete technology, is not an easy technology. And we need to have sophistication, training, and specialists coming into the field. And we're seeing it now as much as ever before. Even construction companies are hiring people with advanced degrees, even PhDs, to come into their operation to provide insight, to understand the results, to help do testing and modeling and so forth. So this idea of our field is led by untrained people just has to be set aside. We need people, we need new students to spend time to understand the problems with a passion, with an understanding of how to do these tests and experience this discovery and the eureka moments to build the future of our field. So I'm saying those words as an encouragement to the younger folks listening to this talk. This is an exciting field with lots of opportunity, and I wish you the best in pursuing that in your own career path. So Eureka, that is the end of my talk. Thank you all for joining me for this last hour, and I wish for you to have a good the rest of the conference. Bye.
Well, good evening. I hope everything's going well at the conference. Hi, Alex.
Good. Thank you for giving that exceptional talk. We'd like to now open the floor for discussion. Are there any questions?
Let me start before the questions come in. Let me start by thanking you, Alex, once again for the invitation to participate. This idea of pre-recording the video, I think it probably does help. The international distance has some complexity at times, and this gave a nice, clean presentation that I don't have to actually go through it myself here. But I hope you enjoyed it, and I'm glad to be with you by Zoom here, by web.
Yeah, thank you for joining. I know it's early in Champaign there.
That's okay. I've got my cup of coffee.
There we go.
I'm going.
Let's see if there are any questions in the
Dr.
chat.
Alex, can you see the chat box? There are some questions there. Can you please see the chat box?
Yeah, go
Yes.
ahead and look, Alex, for me.
Yeah.
If I need to look at the chat box, I can do that too. But maybe if you moderate it.
So here was a question: how to measure strain in a highly nonlinear strain field?
Okay, so the eureka moment that was related to strain measurements was giving several different kind of techniques. If it's highly nonlinear, you get discontinuity. I mean, that's highly nonlinear. That's essentially an opening crack is highly nonlinear. But these techniques that I showed were intended to capture those discontinuities in strain. So they're particularly good. And of course, if it's a big enough crack, you can see it with the naked eye. You can use video or something like that. But these techniques are those very, very, very small cracks that we need a sensitive technique to bring it out. And that's what I was trying to show in that eureka.
Is there any follow-up question on that? It appear not. Here was another question. Are there any tests to measure the real-time changes in pH value that happens when carbonation occurs without damaging the concrete, unlike the phenolphthalein test?
That's a great question, Divya. I would say that's a PhD. That sounds like to put sensors for pH into your microstructure so you can get sort of a real-time, long-term reading is a nice idea. pH is a tough property. The sensors tend to need time to equilibrate. Having long-term embedded sensors for pH, I don't know that they necessarily exist. If they do exist, that'd be a good thing for us to explore. There are long, periods of time in hydration of Portland cement where pH probably doesn't change that much. So maybe that'd be part of the study, would be find special cases like the carbonation case where you're expecting or need to know that pH is in fact changing. And that would be part of the experiment, I imagine. But I don't know that I have any magic bullet on that. We need some advance on that. Sounds like you should work on this.
Our next question, it's a little bit open-ended, but can you please tell us about digital image correlation technology?
Okay, well, digital image correlation is very attractive because it can be used on lots of different scale. Any scale where you're able to take digital images, photographs, and you take a time sequence of photographs, even long term, even over days, it could be in some cases. When you take the set of photographs and compare them to each other, the computer is looking what is changing between time step A and time step B and time step C. If they're not changing, the computer doesn't worry too much about it, but it can identify those changes and discontinuities. And therefore, in say, as we used it in a cracking problem, the cracks are elucidated by digital image correlation. The reason it's an attractive technique is the original acquisition can be as simple as a digital camera. It doesn't need to be complex, but the analysis, is standardized. So you can find these DIC programs and plugins for programs out in the field, and they're pretty powerful. So I've seen a lot of good techniques with DIC over the years. I encourage it. It's a good technique, still is.
Oh, this next one's very good. I'm interested to hear this. I would like to hear your opinion on the area of research in carbon capture, utilization, and storage. What is the long-term implication towards durability of concrete structures, and will this be a feasible practice?
Yeah, I know why you're interested, because no one knows the answer to some of this stuff, how practical and meaningful it'll be in the long term. You might get from the talk I just gave. I'm not necessarily a chemist, so with regard to sequestration, carbon sequestration, and knowing the chemistry of that, and our experiments have not been on that topic. I do think that just as you watch the life cycle of making cement, being used in construction, now decaying, the geologic time frame, things will come back to the sort of an original source. So if we release that carbon dioxide in the manufacture of cement, someday we have the potential in geologic time frame, perhaps, to bring that carbon dioxide back into our structure. So the concept is completely sound. The time frame and how we do it in a practical matter that is a useful technology is a question. And I think it's still yet to be proven, to be honest. I think we have a lot of thinking going on with regard to low carbon concrete, and the economics of it is still yet to be proven out. So, but it'll come. If you have any kind of a technology that justifies economic benefit, I think we can trust our industry that they will take advantage of this. Their industry wants to seek profitability and so forth. And so good ideas will get commercialized. but there's a lot of ideas that are a little bit on the margin, and so we don't see every idea being picked up. So we just need to keep going. And that's where we are right now. I think we have probably more ideas than we do time to implement them.
All right, our next question. What are the I'm wondering if that's implicit, maybe. What are the implicit measures to be taken while blending 2 to 3 SEMs?
I'm not sure I understand the idea there.
Yeah, maybe the person that asked the question can ask a follow-up to maybe clarify that question. Let's go to the next one then.
Well, let me say this about
क्या हुआ मालिक? आने दो यार आराम से।
Can you please unmute yourself, please?
I believe I'm back now.
Am I on right now?
Yes.
Yes, yeah, we can hear
Okay.
you.
This system just kicked me off for a second.
Yeah.
Okay. The point I was generally going to make for us is that SEMs are a great idea in this whole period of time that we're talking about low carbon concrete. Recycle, reuse, these themes are very strong for construction. And if we're thinking about how we can be good, environmentally responsible industry, having effective recycling is, to me, the very number one thing we should be working on. There's a lot of other good ideas, but recycling has to be very high. And we're seeing a lot of people doing that. I tend to promote these ideas in the context of airports, because we have lots of concrete at an airport that's very high quality. And when we remove runways out of service and crush that concrete, that's an outstanding source of aggregate. And we need them to build the new runways and taxiways on the same airport, so we don't have the transportation problem. And so airports is an ideal location to exercise concrete recycling. And the same thing with SEMs. You're using a waste material. The thing there is to make sure that all the SEMs that we're using are in fact truly effective and beneficial for the properties of concrete. We'll see papers about some SEM, some kind of crazy new idea, but in fact the data says it's not actually helping the concrete. It's basically using concrete as a garbage can. We're putting just junk into the concrete. I philosophically am opposed to that. Concrete is a very important structural material. We don't use it as a garbage can. If you can find things that helps the concrete properties, that's a good SEM. But don't put soil into SEM just because you want to get rid of soil. So use the idea of SEMs with responsibility in mind.
Okay, so we had the chat kind of reset. So we have, so I lost some of the previous questions, but the people are writing them back in. So one that came in is, can you provide an insight on digital twin enabling on construction from the perspective of sensing materials behavior, maybe that's characters in real time?
Well, I'm not sure. There's another question. I'm not sure I really understand what the idea is. I don't know what digital twin is.
So digital twin is sort of providing sufficient sensing that you now have a virtual representation of that structure.
Oh, okay. Well, okay, let me just say broad remarks about sensing. this is a fantastic area that we've seen good advances and need more students to be working on. Sensing, embedded sensors, this is a big opportunity. And where we are in the development of these things, they're most often we are seeing these new sensing systems used as sort of a complement to the main experimental methods. But what we don't see them brought into is real-time structural health monitoring. And that evolution to go from the laboratory into the field where they are part of the life performance of the structure is still evolving, still unfolding. And I think there's a good opportunity to do sensor development that can be meaningful and beneficial in servicing the life of the service life of the structure.
All right, another question that came in. What are your views on extra processing methods required to recycle hazardous waste materials, presumably for use in concrete?
Right.
Yeah.
If there are potentially this is extremely powerful. If there are things we can do that takes away the toxicity of a waste stream so that we can safely use this material for a new use, that's a big deal. That's a very powerful. So there could be, I don't know if it's necessarily thinking about radioactivity there, but there are many other kind of waste streams that are rejected because they're toxic in other kind of means. And so we could think about how to neutralize the toxicity to render these other waste streams to be palatable. I think that's actually a nice topic. I don't know a lot about it, but it sounds like a winner idea to me.
All right. Is there any mechanism to measure electrical conductivity, pH, and carbonation in slag or fly ash concrete? No cement concrete.
Well, yes, we use some of the principles of the 4-point method, and so are still, I mean, the principles are still valid. So applying old principles to new devices is a sound idea that could advance our technology for these things. So electrical conductivity, certainly there are valid techniques, established techniques, and pH and carbonation. I mean, that by itself normally needs a laboratory test to determine degree of carbonation. But relating that would be an idea of relating the state of carbonation to something easy to test, like electrical conductivity. We can test that instantly and fast, and we can use embedded sensors to do it. So this might be an opportunity to take an issue of interest to us, like carbonation, and find easy parameters, easy properties to measure, like the electrical properties. And so to the degree those things are possible, again, these sound like PhD studies. So good idea. I mean, that's actually a good theme for development of new technologies. Take a complex property of concrete and find surrogate properties that are easy to measure. And then focus on the calibration problem of taking the easy method and making it insightful for the complex problem. The world needs more of that.
So if there's any more questions, please put them in the chat. If people have more questions, maybe I'll give them some time so I can ask a question. If people have more questions, you can put it in the chat. So David, what do you envision 30 years from now? What's concrete going to look like in 2050?
Well, you know what, Alex, what comes to mind is at the beginning of this talk, I showed some documents from 1970.
Mm-hmm.
And one of the things that we saw is that some of the main themes of research stay constant over generations. So I'm not going to predict that we're dramatically different. Concrete still is going to be concrete. I think 3D printing might advance. There's so much attention to that, and there's so many things that we need to figure out. What we are seeing in the 3D printed structures today have to move ahead to be competitive in all respects to normal concrete structures. But I think some of our systems will remain similar. The idea of using an aggregate composite that's delivered with a hardening matrix, those concepts are going to be there for a long, long time. And but what we can do to the matrix to make it more environmentally friendly, and what we can do to the aggregate side to make it more environmentally friendly, that is using recycled aggregates in these systems. Those are the margins of our technology, on the edge where we can make impact by changing the nature of our constituents, making our process as a whole more environmentally responsible. And but the process itself of casting concrete and making effective structures, I think, will stay intact for generations to come.
Yeah, and sort of a follow-up question there just came in the chat. Is there any scope in recycled aggregates in SCC with 100% cement replacement?
Oh, I don't know about that. Not that I know of. People are trying to find ways to get more cement replacement, but I don't know if I can say that we see ideas of 100%. I mean, you could use things like slag cement. It's another source of a cement that has cementitious qualities. So there are some things about changing out of the cement there. But let me say this in the terms of SCC. Recycled systems themselves tend to be more highly variable. SCC is a system that requires really precise proportioning and control. One of the problems with SCC is that you're really sensitive to your water content, because your water coming in from aggregate sources and so forth it affects workability, and you've got just everything has to just work perfectly together to get good SCC. So what do you not want to do? Use a highly variable constituent. I mean, if you're trying to make SCC and hold everything together just so, don't use a constituent that is crazy variable. And so recycled materials we need to find better technology for standardizing the performance and the quality of a recycled particle. The crushing operations have to deliver just a good, reliable particle size distribution. The water content has to be measured in process, in the flow. All these things need process control. So, and if you can control these things, then you could do something as sensitive as SCC. I'd say that's, you're trying to make life difficult when you're doing SCC as your target.
Good. We have some more questions coming in. What is your view on using bacteria in concrete to impart self-healing?
Okay, I actually kind of like this question. We've seen a number of studies about this self-healing. I like the self-healing if your objective is to create a watertight structure. I like self-healing a lot. And the bacteria is a very viable concept for closing off the pores from water movement, which is a big part of our problem. What it is still yet to be proven is that you can restore structural performance of the material with self-healing concepts. I think that intrinsically you can't exactly do that. When you're trying to create adhesives that replicate the properties, the structural properties of the mass, it's hard to do that. Filling the gap, no problem. I believe that can be done. But creating strength across an open interface is a different kind of a problem. So I think that we want to probably moderate our expectation that self-healing can restore strength and can restore, say, ductility. I doubt that it really can, because of the nature of what it means to fill cracks. But to restore water tightness, yes, I like that idea. And therefore, you're thinking about durability, long-term service life of a structure. Those things can be accomplished. Cutting down on the corrosion of steel, those things can be accomplished.
All right, next question. Why are recycled aggregates acid washed?
Well, I guess that's probably, I'm thinking about how we use muriatic acid to remove cement paste. And it's probably that idea that we're trying to remove the friable material on the aggregate that diminishes the bond. So the acid wash is a way to remove cement paste from the outside of aggregates. I'm not sure I like that idea though. That's environmentally expensive. I mean, you're creating acids, and that's its own kind of an issue about maybe the solution is worse than the cure. So I would say what we want to instead to do is find ways to do crushing effectively so that we have aggregates that have a degree of soundness that they become viable sources for us for making concrete, rather than acid wash. But I mean, I think I understand why someone would suggest that, but right now I'm not so sure. I think it's a great idea. You know what it could be a great idea with? It could be a great idea if you have an industrial waste product with acidity. That could be an interesting thing where you're trying to solve the disposal of acids and combining it with the need to improve crushed aggregate particles. Maybe there is a usefulness to the idea in that context.
Can we find the rheological property of cement mortar using vane shear test apparatus, which is used for soil instead of using a rheometer?
Yeah, you know, this idea, I'm going to broaden that. Can we borrow techniques from other fields to give us insight in our materials? I made my whole life on doing that. That's the thing we've done a lot. And we've seen it from one of the earliest examples I gave was finding modeling in metals that were developed in the 50s. This is post-World War II materials research gave us insight into the crack propagation in concrete. And we borrowed that whole field. Concrete field, borrowed it from the metals field. And Irwin, you know, we use this Irwin model for cracking. He was out of the steels. He was employed by the U.S. Naval Research Lab to work on high-strength steels in shipbuilding. And we use his model in concrete. So there's a good example where borrowing from other fields is a good shortcut. You benefit from this. Is all part of reading the literature. Reading the literature, not in just the field of cement and concrete, reading the literature across material science can get us far. We should train our students to do that even more.
Can you share your views about Vedic plastering material?
What kind of plastering material?
Vedic, V-E-D-I-C. I'm not sure what that is, to be honest.
Yeah, I'm not sure what that is either. Other than just to acknowledge that there's a wide range of cementitious materials that share in common many of the fundamentals. We have hard aggregate, you know, inclusions in the mixture. We have a bonding, a binder that sets and hardens. So the principles in a mortar are often the same principles we have in concrete. And so let's bring them together. Conceptually, as a scientist, they are very similar materials.
Yeah, the person who asked that question has a follow-up regarding that one. Please put it in the chat. All right, next one. How much do you think engineers and manufacturers should focus on implementing eco-friendly ideas to construction rather than conventional methods? This is because we know carbon emission is a very big deal.
Right. Well, the topic of carbon emissions and low carbon concrete is taking the world by storm right now, and so academic researchers often kind of follow the money. So you go to places to do that have funding for the research that you are interested in, and right now the topics surrounding low carbon concrete are very popular. So I think it could be that national funding agencies would be very open to support research, more research on these topics, and therefore this is an opportunity to pursue it. So there needs to be a partnership between policymakers who basically drive the flow of research dollars and researchers that bring the possibilities to the community. And at some point, they're going to meet in a zone that defines the research topics that are popular in the day, where we have the meeting place of funding with minds, and we can solve these problems.
Unfortunately, I've been told that the time is up for the session. I know there's still questions in the chat, so I apologize we didn't get to all of them. But let me be the first to thank Dr. Lang for joining us today and giving this exceptional talk and having an exceptional question and answer session. I'll turn it over then to who's next? Blesson, I believe.
Yeah, thank you, everyone. I appreciated being here.
Yeah, comparing team, please.
Thank you, Dr. David Lang. It was indeed an informative talk. We got to learn about so many eureka moments, and after your talk, we're expecting many more to come up. And thank you for patiently answering all the questions as well. So please accept the memento from our behalf as a token of appreciation. Thank you.
Thank you.
Thank you, sir. And I also extend gratitude to Dr. Brandt for your valuable time and sharing the session. It was a pleasure to interact with you too, sir.
Yes, thank you all. Thank you, Blesson.
Thank you, Dr. Lang.
So with this, we have almost come to the end of today's inaugural session of ICCMS 2022. I would now like to invite Dr. Miriam Vele-Lizancos, convener of ICCMS from one of the organizing institutions, Purdue University. She is an assistant professor of civil engineering at the Purdue University, USA. She holds a PhD in civil engineering from the Universidad de Corona, Spain. She leads the Vele Research Group, whose goal is to reduce CO2 emissions and contribute to stopping climate change by creating sustainable, high-performance construction materials to preserve the world and new materials for the present and the future. I welcome you, ma'am, to propose the vote of thanks.
Yeah, thank you so much for the introduction. And well, before starting these final remarks or thanks for everyone, I want to thank Professor Lunch because I really enjoyed the discussion that we have had. Very, very interesting one. So. Well, first of all, in the name of the organizers, I would like to thank the plenary speakers and their great contribution to this conference. Professor Lunch from University of Illinois, also Professor Ravindra Getu from the IIT Madras, Professor Laura De Laurentiis from ETH, Professor Moheb Beni from McMaster University, and Professor Susan Bernal from University of Leeds. It's a great honor to have you all. And, we already enjoyed the first plenary talk, which was amazing. So thank you very much all. Also, we would like to thank all our amazing keynote speakers that we'll have over these days of the conference. I mean, these are all great researchers from all over the world. I think this is an amazing team, really. So thank you, plenaries and keynote speakers, because we have, thanks to you, more than 500 participants registered, and today we had over 300 online. Right now not, because there was a glitch, but before this glitch that we have a few minutes ago, we have over 300 participants online, which is great. I would also like to thank everyone involved in the organization of this amazing conference, including the 7 universities that had organized, co-organized this event, and all the collaborators that provided technical support, such as the Indian Concrete Institute, the RILM, and the Institution of Engineers in India. So thank you so much all for being here. I mean, it's amazing what you have done. And I want to finally highlight the leadership and persistence of Dr. Blessing, because he was a great organizer and have worked tirelessly to get this ready to go. So thank you very much, Dr. Blessing, for all your work and also your patience. So I think that's all from my side. And again, thank you so much, Professor Lunch, because that was an amazing discussion.
Yeah. Comparing
Thank you, Dr. Thank you, Dr. Willie Lisankos. I hope today's session was constructive and beneficial to all of you. I extend my gratitude on behalf of the ICCMS 2022 committee to all the distinguished professors, speakers, invited guests. It was an honor indeed to have such eminent professionals, and it was a pleasure to have interacted with you. Thank you for taking out your valuable time. I also thank all the participants, and I would like to quote, "Just remember to never doubt yourself. We are all capable of amazing things. Keep learning, listening, growing, and experimenting." So with this, we come to the end of today's inaugural session. I look forward to meet you all again tomorrow at 8 a.m. Indian Standard Time. We have interesting keynote sessions lined up for you. Thank you and stay safe. God bless you all.
Yeah. Thank you, everyone. So you can leave the session, and I'll be sending the details about the tomorrow's session by email. You can join according to the schedule. So the first session starts at 8 a.m. Indian Standard Time. Professor Anurag Mishra from Indian Institute of Technology, Jammu, will be giving the first keynote session. So please be online at right time. Thank you all. Thank you, Dr. Marian. Thank you, Dr. Alex, and thank you, Professor David Lange. And thank you, the comparing team. Thank you, everyone.
Thank you so much.
Thank you.